right, so let's get going here. It is like genuinely my pleasure to welcome my dear friend Thankful to give this week's colloquium. She'll be talking to us about all things pulsars. And I tried to promise Thankful that I wouldn't be too sappy in my introduction, but she is truly like one of the best people I know and one of the best scientists. She did her undergrad at UNC and then did grad school with me at UVA in Charlottesville. After that, she went to Cornell with a Hubble Fellowship and worked with Jim Cordes and Shami Chatterjee. And then now she's at the Naval Research Lab in DC, working on some really cool gamma ray timing of pulsars. So I would like to thank Carnegie for flying my friend out here. And thank you, Thankful, for coming.
They're going to think it's just nepotism. This is terrible. Thank you, Allison. So hi, everyone. Thank you so much for having me. I do really appreciate it. It's my pleasure to be here today and talk to you about some things that have been going on in the world of pulsar timing array work. So we can go ahead and get started. I always go back and forth a little bit on how to start these talks. Do we talk about sort of the interferometer as a whole, or do we talk about the elements of the interferometer? And so today I'm going to start talking about the pulsars themselves, because I come at this from the perspective of a pulsar astrophysicist. So we'll go ahead and start there. Very, very brief introduction, right? So very massive stars can undergo core collapse supernovae and turn into neutron stars. These are something of like a failed black hole, right? Not quite massive enough to turn into a black hole, but what you get at the end is an extraordinarily dense, sort of city-sized remnant. The discovery story is quite interesting. In 1967, a graduate student named Jocelyn Bell-Burnell was doing a completely unrelated project with a radio telescope that she had helped build, and saw from a very specific part of the sky at the same time this pulsing that was very regular, these little blips. And so originally, or initially, they called these LGM, for little green men, because the signal was just so regular that they were joking about it being man-made or perhaps extraterrestrial made. Of course, no one actually believed that that's what they were seeing. And it turns out what they were seeing were pulses from a spinning neutron star called a pulsar. And I do like to mention, just for the sake of students, Dr. Bell-Burnell was sort of snubbed for the Nobel Prize. It was awarded to her advisor and department head. She has never sort of expressed anger about that, but it is worth noting as a very unfortunate part of the history of pulsar science. Okay, so pulsars are a subset of the neutron star population, right? They beam radiation out of their magnetic axes as they spin around. And so you see it as sort of a lighthouse. You see it ticking. And pulsars don't pulse intrinsically, right? It's just an effect of the fact that they're spinning. And so, I already mentioned they're city-sized. They weigh something between 1 and 2 solar masses, but that's actually something we'll touch on again near to the end of the talk. Millisecond pulsars are a very special subset of the larger pulsar population. So these spin extremely rapidly because they've been spun up by accreting matter from a companion, so that you have these very circular sort of lower magnetic field binaries with a white dwarf often and a neutron star, a pulsar that's spinning extraordinarily rapidly, so at millisecond rates. These are very steady spinning sources, right? So they take a really long time to spin down. Their pulse periods don't change very much over time. We know of about 400 of them. It's more than 400 at this point. We know of more than 4,000 normal pulsars, so slow pulsars. And these are technically or generally thought of as radio objects. So objects that are best studied, they're very steep spectrum at low frequencies, right? So we use radio telescopes, large single dish radio telescopes, especially like the Green Bank telescope, the Arecibo telescope before its collapse, and many other instruments, but we can also observe them with interferometers. And I'll talk about facilities a little bit later. But this is sort of the picture, the basic picture of millisecond pulsars, these objects that we're using for pulsar timing arrays. So the reason why we care so much is that they can be used for a process called pulsar timing. Pulsar timing basically describes the process of accounting for each and every rotation of one of these pulsars. So you can imagine that if the pulses were sort of arriving at very, very regular intervals, there was nothing kind of intervening to stop them, it'd be quite easy to come up with a model that describes the predicted time of arrival of every pulse. But the reality is much more complicated. There are a number of factors that make the pulses not arrive at a perfectly regular interval. And these are all of the things that we have to take into account when we're trying to construct a model that properly predicts the time of arrival of each pulse. So Dr. Bell-Burnell's kind of original pulsar was visible by eye on a strip chart recorder. But that's not the case for the vast majority of these sources. In fact, we have to integrate up a bunch of individual pulses in order to get the steady pulse profile. So even though the profile of individual pulses might jitter around quite a bit, over time, the pulse profile, this integrated profile that you see on the left there, stays quite steady. There is, for a lot of sources, some evolution in frequency, but over time, most of the time, the pulse profile is not changing all that much. So all of the things that can make pulses not arrive on time. We think about things like period derivative, things that you have to take into account when you're initially making a timing model for your source. If it's in a binary, you have to have a Keplerian parameterization of the binary orbit. There are things like dispersion measure. Pulses are dispersed by a 1 over observing frequency squared. And so you have to kind of realign the signal before integrating, or else you'll get a totally smeared out profile. We call the differences between the predicted time of arrival and the measured time of arrival a timing residual. You can see on the top left what it would look like if your timing model is doing a pretty good job of predicting the arrival times of all your pulses. So there's not very much structure. There's nothing, sort of obviously wrong. It's kind of scattered around zero. It's looking okay. But if, for example, you had a small error in the spin down rate of the pulsar, it would induce this exponential curve in your timing residuals. That would be a very obvious indicator that you need something else in your timing model. Same thing for like getting the position wrong, right? That's going to induce a yearly sinusoid. The proper motion being wrong induces this kind of growing over time signal. And so, we're looking for a timing model that takes into account all of these different factors and correctly predicts when each pulse will arrive. The reason this is so cool is because pulsar timing, this accounting for individual pulses, gives us measurements that rival atomic clock precision. So this is what we knew the period of J1713 to be. Not right now, it was like a few years ago, probably. I should update this slide. But the precision that you get from this technique is truly incredible. Okay. I'll talk just very briefly about the other kind of more complicated processes that are also involved. For pulsar timing array work, which is what we're talking about today, you need really phenomenal timing precision, less than a microsecond. And so you have to take into account the various noise processes. There are white noise processes like instrument noise, pulse jitter, which I talked a little bit about. This is individual pulses not staying stable. Red noise processes like intrinsic variations in spin period that some pulsars just show. There are, very complicated ways of kind of modeling dispersion measure, red noise processes, chromatic processes like that over time that you also have to take into account. And so, we have to do this very careful accounting because we need to reach the precision that you see on the top left. So that very small width, this is an integrated profile up here, that very small width is about 1,000 times the precision that we need to measure our TOAs with. And so this is basically just to kind of show how important it is to get all of these little things right, because the gravitational wave signal that we're searching for is going to be quite subtle. So a very quick introduction to these pulsar timing arrays. We'll step back for a second to normal sort of electromagnetic astronomy. We know that there's a wide range of frequencies, about 20 orders of magnitude, over which you can do all kinds of exciting observations, right? And depending on what frequencies you're conducting your observations at, you're going to be sensitive to different astrophysical processes, right? And so the difference that you're seeing between like gamma ray data of a certain source and radio data of a certain source, it's going to give you sensitivity to different things that are happening. We all know this. But we love now over the last, I guess, 8 or so years to talk about this new window that's been opened up by gravitational waves. And it's a little bit analogous to the EM astronomy I mentioned. So about 100 years ago, this, classic GR proposition from Einstein, we know that mass curves space and space moves mass, right? And one prediction is that accelerating masses will create ripples in space-time that propagate out at the speed of light, and these are gravitational waves. So gravitational waves are polarized in the plus and kind of cross direction, we think, probably. And we refer a lot to the strain. So this is the amount that the gravitational waves are actually stretching and squeezing space-time. So some amount of change over a nominal length, that's the delta L over L, and we call that H, or the strain. And so I'm going to refer to that quite a few times. But detecting gravitational waves is not something that was thought of 10 or 20 years ago. People have been thinking about this for a long, long time. So starting in the 60s with this famous resonant mass detector, you can see a picture of it on the left. There were propositions for sort of spacecraft-based detections of gravitational waves. But the most relevant ones to us were in the 70s and 80s, and especially the prediction from Hellings and Downs in 1983. And so that was shortly after the discovery of the first millisecond pulsar, first pulsar that sort of had a stable pulse period and could be measured and timed with high precision. So we talk a lot about that Hellings and Downs paper. The first indirect detection of gravitational waves was from the Hulse-Taylor binary in 1974. That was the discovery date. The Nobel Prize for this work was awarded in 1993. And basically, it was showing the energy loss, the shrinking of the orbit due to gravitational wave emission. And so this was done over a period of many years. And you can see the GR prediction and the actual measurement of the change in the orbit matching quite well. It's a very beautiful result. And so this is not a direct detection of gravitational waves, right? But it is sort of a very good hint that that is what's taking energy away from the system. And as we all know, of course, LIGO's first direct detection of gravitational waves in 2015 and of neutron star mergers after that. LIGO is sensitive to sort of tens of solar mass black holes and neutron star mergers and events like that. But this was a very beautiful result, and it really, as we know, kicked off this kind of era of new windows into the universe, this gravitational wave window. So this is sort of what that looks like, right? This is analogous to the normal EM spectrum we saw at the beginning of this section. Here at the high frequency end, you have LIGO type experiments, Virgo, Kagra. These are sensitive to objects that are emitting gravitational waves that are not as massive, right? These are lower mass objects. They have pretty, fast event rates. So the amount of time that it takes for the binaries to coalesce is quite short. And so the amount of strain that you're dealing with in these systems is quite low relative to the other kind of experiments that we're going to talk about. In the middle here is LISA. That's going to launch next decade, we hope. It's going to be sensitive to sort of intermediate mass systems, very high mass ratio binary and spirals, things like that. That's going to be extremely exciting. But then what I'm here to talk about is the very low frequency end of the spectrum. And so this is pulsar timing array experiments. And pulsar timing arrays are dealing with much higher strain amplitudes. So, our sources are quite different than what the sources are at the higher end of the gravitational wave frequency spectrum. We are sensitive to the in-spirals of supermassive binary black holes. And so this is what we think are at the centers of all galaxies. And so what we're probing with this sort of technique is galaxy growth over time. And so it's a very unique probe. It's very complementary, I would say, to like LISA and LIGO. It's just a completely sort of different type of experiment, even though it's kind of working on the same principle. And you can see if we included primordial gravitational waves at much, much lower frequencies, we would span a kind of similar 20 order of magnitude range as EM astronomy, which is kind of neat. Okay, so we're going to look at pulsar timing arrays in a couple different ways. Hopefully it will convey kind of what they look like. We know that our sources are these supermassive binary black hole inspirals. These are happening all over the universe. Kind of the first signal we expect to be sensitive to is an ensemble signal. So the combination of all of these different galaxy mergers going on all over the place. And then that signal is going to propagate through the Milky Way, where we are timing dozens of millisecond pulsars to extremely high precision. And these are all, relatively local, right? We're not observing pulsars that are outside of our galaxy or anything like that. These are ones that can be timed very well and are relatively close by. And so you're looking at all of these pulsars as frequently as you can, using various radio telescopes, and in the future, not radio telescopes as well, which is pretty neat. Here is a little bit of a video kind of look at what the NANOGrav array actually looks like. But it plots the positions of all the pulsars that we time. And so it's kind of a neat look in the context of the Milky Way. And so it's this network of dozens of millisecond pulsars, all of which we observe roughly monthly. It's quite a sort of complicated experiment, but that's what gives us the sensitivity to those low frequency gravitational wave signals from much higher mass objects. So the first goal of pulsar timing array experiments is to detect that ensemble signal I talked about, the gravitational wave background. And this is the sort of orchestra of all these different supermassive binary black hole inspirals that are going on all over the world. All over the world. What a stupid thing to say. All over the universe. And so, it's not quite the same as like what LIGO's seeing, right? Which are individual continuous wave events, even though we expect to gain sensitivity to those kinds of events in the future. I already mentioned that the gravitational waves are passing through the galaxy, and they're causing the path length between our pulsars and the Earth to change very slightly. And the very important thing is that depending on the angle between all of these different pulsar pairs, the degree of the correlation of that stretching is going to change. And we call that the relationship, we call that relationship the Hellings's and Downs curve. That's what you can see at the bottom right. So it is the amount of correlation in the arrival time change as a function of angular frequency. And so that is sort of the smoking gun kind of indicator that what you're seeing is actually a gravitational wave signal. It was predicted quite a long time ago, as I mentioned, in the 80s. And this is kind of our goal. We want to see that as a function of angular pairs, we are seeing a Hellings's and Downs-like signal. Why do this, though? I mean, we need to motivate this work, right? So the purpose is to study how galaxies kind of merge and grow over time. We'll look in just a second at kind of what we can actually learn astrophysically from pulsar timing array work. But the general sentiment is just that we want to know how mergers proceed, what the environments in which these mergers are happening are, and do we think that they're stalling out at a certain distance? Do we think that all of the supermassive black holes are much, much less massive than we expected? Who knows? But there's a lot that we can learn by looking at this gravitational wave spectrum. And as I mentioned, we hope later to gain sensitivity to different kinds of signals, especially continuous waves. So these are going to be individual mergers where we know, this is the merger that we're looking at. It's not that ensemble signal anymore. Okay, don't worry too much about the equations. I just want to point out a few things that sort of determine what we're looking for when we look at these gravitational wave spectra. So the strain spectrum is a function of the amplitude of the background, and then this spectral index alpha, that is a prediction from quite a long time ago at this point, Finney 2001. And it basically predicts that the value is going to be -2/3. This just assumes that all of the different mergers that are happening all over the universe are circular and equal mass and sort of very basic. So a little bit of deviation from that measured spectral index isn't terribly surprising, but that's kind of the baseline we're starting with. And then the other thing I want to look at is this cross-power spectral density, because it kind of highlights one quantity that's very important. And the only reason it's important is because it explains why these experiments work, I think. So this overlap reduction function gamma that you can see it's a quadrupolar function, right? And so you can pick apart different kinds of contributions to your gravitational wave signal because they are going to induce different kinds of sort of shapes in your gravitational wave spectra. So if we had, just clock errors, if we had, all these observatories have different corrections to GPS time that they need to make, if there was just some wandering clock or something, that would induce a monopolar correlation. If we had an error in our solar system ephemeris, right, as the Earth goes around the sun, you would see a dipolar signal induced. And we actually did see something like that quite a while ago at this point. But it was really interesting because it was telling us, hey, the mass of Jupiter is a little bit off. And you're actually able to see that in your signal. And so we had to go back and forth with folks at JPL working on these ephemerides and kind of learn how to compensate for the fact that we really do have this kind of sensitivity. And that's really neat. It was stressful, but in retrospect, it's very cool. Yes?
Okay, so how long was the mass?
That's a really good question. I don't have a number for you. I'm not sure. But I do know that
So like percent, or is it percent? Like where is that concert for ballpark order of that?
I'm not sure. I'll look it up though, and I'll let you know.
Thank you.
Yeah.
All right.
Yeah, sorry. Okay, so what you're looking for in these gravitational wave spectra, these are just two of the kinds of things you can highlight to get a grip on what astrophysics you can extract from these results. So one thing you can look at is where this power law turns over, right? And so this is going to be better kind of characterized once we have more observations. This is not something you just get right off the bat with some kind of detection of gravitational waves, of low frequency gravitational waves. But with time, as you gain more sensitivity to those low frequencies by waiting a longer time, you can see that if there's kind of more spectral turnover than you expect, that can tell you something about the actual way the mergers are proceeding, whether or not they're stalling, what the mass distribution is. The amplitude of the signal, right, can just tell you about the rates. So how many of these events are contributing to the overall gravitational wave background signal and other kind of related quantities. And so this is not comprehensive, obviously. It's just trying to give you a sense that there are pieces of astrophysics that you can extract from the characterization of the spectrum. Okay, so I'll talk a little bit about the NANOGrav collaboration. NANOGrav, I've mentioned it several times, but it's the North American Nanohertz Observatory for Gravitational Waves. We've been doing this for quite a while now, since 2007. We are funded through the NSF as a Physics Frontier Center, and we have more than 80 institutions now and more than 180 scientists and students who are contributing to our work. So it's really wonderful. It's a very large collaboration. We use the Green Bank telescope, the Very Large Array, the CHIME telescope, the Canadian Hydrogen Intensity Mapping Experiment. And until recently, obviously, we were very heavy users of Arecibo. And so we were, for both scientific and personal reasons, very affected by the loss of that instrument and are, so sort of having to still deal with its collapse. NANOGrav is just one part of this larger international collaboration called the IPTA, the International Pulsar Timing Array. We have colleagues in Europe, in South Africa, India, China, Australia, all using their own wonderful instruments to do sort of similar work. But there are obviously lots of sort of subtle things that you have to take into consideration from telescope to telescope. And so the goal is to combine all of our pulsar timing data sets together in order to gain more sensitivity to the gravitational wave background. That is the ideal. The reality is that it's a very hard process. We all have our own little ways of dealing with various kinds of noise and, as I mentioned, different kind of subtleties in our data. And so this is something we work really, really hard on, but it is a very difficult process. So right now, NANOGrav is sort of still dealing with the loss of Arecibo. We lost about half of our sensitivity to the gravitational wave background with the loss of Arecibo. So we had to restructure the observing program. We have GBT monthly observations of almost 80 millisecond pulsars. 18 of those are being observed both at 800 megahertz and L-band. And then the rest are only observed at L-band because we're able to use CHIME, which I mentioned. CHIME has a bandwidth of 400 to 800 megahertz, and so it helps us get that low frequency end. And we get daily observations, right? Which is extremely cool. Having that very high cadence gives us more sensitivity to different kinds of events, like continuous wave events. But we also have the VLA. So the VLA isn't quite as large a proportion of our program, but we have 15 pulsars that we time at higher frequencies. Some pulsars do emit quite strongly at higher frequencies. I say high frequencies, I'm talking about S-band. So if there are radio observers, you know that that's actually not all that high frequency in the radio world, but all but one overlap with the GBT source list, and that's because we can see far enough south of the VLA to get a very important pulsar called 0437. Okay, so this sort of just shows the growth of the data set over time. In 2013, we published the first NANOGrav data set, Demarest et al. It had 17 sources, and it sort of obviously time on the y-axis, pulsar additions on the x-axis. And you can see that we sort of slowly but surely grown the data set. And there are obviously going to be jumps depending on, how many pulsars we were able to add for kind of time constraint reasons and new pulsar discoveries. All kinds of things go into our source selection process. But our most recent data set that we published in June of this year was called our 15-year data set. And so this added 21 new pulsars over our last release, which was the 12.5-year data release. And you can see, like for the 12.5-year, we only added 2 new sources, but we don't have a ton of control over that. But by this point, we had added enough sources and we had observed them for long enough that we were able to sort of substantially make a jump in the number of pulsars we timed. So here's just a flipped, yes. Here? Yeah, very good question. So there was a misbehaving local oscillator at Arecibo. So for the pulsars that we only time at Arecibo, for about a year and a half, there was a little bit of like jumping from that local oscillator. And so when the signal got mixed, it got dispersed wrong. And if you're dispersing at the wrong DM, you're going to get smearing in your pulse profile. And unfortunately, this is like a to-do item for us, is to see if any of those data are salvageable. We're working really hard on that. It's a very hard problem because the kind of severity of the impact varies a lot from epic to epic of observations. And so it's hard to say, like, at what point are we going to be satisfied that there's not too much contamination? We'll probably have to have separate noise parameters for that period of time. For those pulsars, and so it's a little bit of a complicated thing. But for this data release, we just had to kind of chop it all out. Yes?
Are the new pulsars that are being added now fainter than the ones you started with, or is it just searching other parts of the sky?
Yeah, for the most part, they are. Most of the low-hanging fruit is done, right? So we're not adding kind of any whoppingly bright sources that we just haven't been timing. There have been a lot of reasons why we've been able to add so many new pulsars. One of them is these Fermi gamma ray directed searches. So you can kind of choose unidentified objects in gamma ray catalogs and say the spectrum looks very millisecond pulsar-ish. Let's go back with our radio telescope. We can do a single pointing on that spot and see if it's a pulsar. That's been extraordinarily productive. And so especially over the last 7 to 10 years, we've been able to add a lot of pulsars that way. But yeah, it's a good point. That's one reason why we're going to be so reliant on kind of new instrumentation, because we really need to be able to time as many pulsars as we can. And you know, we are having to add kind of fainter and fainter pulsars to the array. So this 15-year data set had, oh, sorry, I should step back and say, from the analysis of the 12.5-year data set, we saw a common red process signal, a noise process in all of our pulsars that had, you know, a shared spectrum, but no evidence of angular correlations. So that sort of smoking gun was not present. We didn't see any kind of, you know, as a function of angular separation, any kind of change in the correlation of the timing residuals. But we did see that there is this kind of hum among all of our pulsars. And so that was very exciting, because that's exactly what we expected kind of on the road to making a detection of gravitational waves. So we are using totally new timing software and a totally new pipeline that I'll mention very briefly. I promise I won't go on about it. This data set has 16 years of data. Don't ask why it's called the 15-year data set. It's the first time we included VLA data, which is very exciting. So we have data on 0437. That's this kind of like awkward pink one right here. And you know, we chose the end of the data set to correspond to the last date that we could observe with Arecibo after there was the initial cable break, as well as a change in backend that we were using at the GBT. So I won't go on about this, but there are only a handful of pulsar timing software packages that are used commonly. And so Pint is this kind of new software package that was developed totally independently of the kind of classic two, which are Tempo and Tempo 2. So Pint means Pint is not Tempo 3. You can go check it out if you're interested for some reason. But it's very cool. It's very modular. It's a lot more sort of approachable for students. There's a lot of active development going on for Pint. So it's been really phenomenal to be able to switch over to that. But that means, you know, we've also been working on building a new pipeline, because as we add more and more pulsars, the process of timing all of them gets very onerous. This is not the kind of thing where you can just like plug in new data and hope that the timing model adjusts accordingly and then like say you're hands off. It's a very hard process. Part of that is like determining if there are new timing parameters that are gaining significance. Like, are we able to start detecting, you know, GR effects in the orbits of some of our pulsars? We need to adapt to sort of new timing techniques that I didn't mention, but we're working on ways to kind of reduce the volume of our data set. And so we've had to adapt the pipeline to that. You can check out the pipeline as well. It's called PintPal. We're really trying to go for transparency and accessibility to students and people outside the field, just because there are a lot of eyes on what we're doing right now. And so we want to make sure that everything is quite transparent. And I mentioned this already very briefly, but the reason why we care about this, the reason why we care about adapting to having tons of new pulsars is because that's the best thing that we can do for our sensitivity to the gravitational wave background. So you can see that it is, you know, the number one factor. The amount of time that you've been observing, that matters. The precision with which you can time your pulsars matters. But it is a one-to-one dependence how many pulsars you're actually timing. And so that's what we really care about. Okay, I am absolutely running out of time. So I'm going to fly through one of the synergistic science cases. So this is not part of the kind of normal, I guess, main NANOGrav results, but there are 1,000 things you can do with such a rich kind of long-term pulsar timing data set. One of those things is measuring the masses of your pulsars extremely precisely. And so the reason we care about this is constraining the neutron star equation of state. If you find more and more high mass pulsars, that means that you can say any equation of state proposition is going to have to kind of account for a neutron star that's this massive. And so it's a very kind of simple way of ruling out various equations of state. And this has been an area of a lot of interest. One of the ways we can do this is with a post-Keplerian effect called Shapiro delay. This is what happens when a pulsar goes behind its companion along your line of sight. The companion is deforming space-time. It's causing the signal to arrive later than expected. And the kind of range and extent of that change in the pulsar timing residuals that you're getting can be just combined. So I'm not sorry, I don't want to get into it too much, but these range and shape parameters can be combined with the mass function basically to get out the mass of the pulsar and the mass of the companion individually. And that's not something you can do without those significant post-Keplerian measurements. And so it's a very powerful technique in that way. There's some exciting results from this. There was Demarest et al. 2010. This was kind of the first 2 solar mass neutron star, which wasn't necessarily expected. These measurements have been revised slightly over time, but it put pretty significant constraints on the equation of state. It ruled out sort of some of the more exotic equation of state models. We also had this Cromartie et al. 2020 result with a very massive neutron star, JS40. We have been continuing to observe that source in NANOGrav, and we had a bunch of targeted observations that helped us better refine the mass of the object. And so this has been a very productive kind of synergistic science thing that NANOGrav's been up to. Okay, the main science results from the kind of June release that I mentioned earlier. There are a lot more papers than this, but we're going to fly through all of these various results. I'm not giving any of them any of the time they actually deserve, but I just kind of want to give you a sense of each step of the process and what we're learning from each of these different, kind of efforts. I will mention, I am, as I mentioned, coming from the pulsar timing side of things. I'm the chair of NANOGrav's pulsar timing working group right now. So that's what I'm most familiar with. But I have colleagues working on the actual detection of the gravitational waves, on the interpretation of the astrophysical results, on exciting kind of new beyond the standard model physics topics, and 1,000 other things. So there are tons of interesting science projects being done within NANOGrav. Okay, so this was very cool. I want to emphasize that when we made an announcement in June, it was not a detection of gravitational waves, right? It was evidence for a background of gravitational waves, for a reason I'll mention in a minute. But it was very exciting. This is kind of what we've been trying to do since 2007. It's by no means the end of our experiment, but it's kind of just the beginning in a way, right? We have kind of significant evidence for those angular correlations in the timing residuals, which means that we can be pretty confident that what we're seeing is the gravitational wave background. It was very fun, but this wasn't just kind of a NANOGrav party. All of our IPTA colleagues also released results that I'll mention in a second on the same day. So it's been a wild ride for us. It's been very cool. So really quickly for the timing side of things, synergistic science results, we did mass measurements where we're just continually refining the precision with which we can measure the masses of our pulsars in our pulsar timing array data set. I don't have to get into the kind of individual changes. There are some interesting borderline, quite massive sources that we're following up in separate timing campaigns that are targeted by orbital phase. So we want to look right at conjunction in order to better measure Shapiro delay. So we're doing that for the ones that are kind of potentially very high mass. We also do astrometric parameter measurements. Allison's very familiar with that. And so there's lots of kind of interesting stuff you can do with the data set. If you're interested in learning about noise in pulsar timing array data sets, I highly recommend checking out this paper. It's kind of a front to back description of all of the different things we think about when we are talking about accounting for noise. We call it our noise budget in pulsar timing arrays to make sure that we are narrowing down just that quadrupolar gravitational wave signal. It has a really good discussion of how we do our red noise modeling for the pulsars that need it. And it's kind of beyond the scope of this talk, but it's very interesting. So this is the main kind of result, right? This is the evidence for a gravitational wave background that we have. And you can see, if you remember the shape, the Hellings's and Downs curve, what we see is in quite good agreement with that shape. I know that's sort of a simplistic way of looking at it, but that's it. And so this was a very exciting result to see. You can also see sort of the measurement of the amplitude of the gravitational wave background, as well as that spectral index that I said was minus 2/3 from theory, but we expect a little bit of fluctuation in that. There are all kinds of, both Bayesian and frequentist analyses that are done as part of this process. They are in agreement. You can do different things with various different kinds of analyses. They use 67 of the 68 pulsars because they have a different cutoff for the amount of time they want a pulsar to be timed for. The common process signal that I mentioned that we saw for the first time in the 12.5-year data set, the Bayes factor is 10 to the 12 for that. So that's an extremely significant detection of that common red noise process, so common spectral process in all of the pulsars that we time. But it's also the first time we have compelling evidence for those Hellings's and Downs quadrupolar correlations. And so we're talking about, I said that there are a couple of different analyses that are done. We're basically talking about something from the 3 to 4 sigma range, if you want to think about it like that. So we're quite confident, but it's maybe not meeting that gold standard that folks want to see. So this is why we are calling it evidence for. It's very kind of political, but we thought that this is the best way of doing things. A lot of people ask kind of, how do you know you're not wrong? One of the reasons is because we're very careful about kind of going through all of the different things that could go wrong. One of those things is that the timing group produces split telescope data sets. So trying to kind of isolate any processes that might be going on at the individual telescopes that we use to make sure that those aren't creating some spurious signal. And we see in this distribution down here that both the Arecibo and the GBT data are in quite good agreement with the overall analysis of all of the pulsars, not just the pulsars that are timed at one telescope or another. The other reason is just because this Hellings's and Downs signal is so unlike anything that is produced through other processes, right? I already mentioned when we were looking at that overlap reduction function that we can pick out when we're seeing, a dipolar correlation or a monopole in our signal. It's distinguishable. And so we're quite confident that what we're seeing is the gravitational wave background. The other reason we're pretty confident is because all of our colleagues in the IPTA are seeing very similar signals. And all of our kind of analysis pipelines, all of our processes are quite independent. We're not all using the same software. We're definitely not using the same telescopes. And so if we're all starting to see the same process, obviously we have different sensitivity to the background because we have different, different instruments that we're using. We have different numbers of pulsars that we can time, different observing cadences, but we're all seeing essentially the same thing. And so that's really exciting. That's kind of like, I'm not sure. I find that very compelling, and I think most other people do too. So getting into the astrophysics a little bit, you can tell that the amount of text on the slide will grow with my level of discomfort with the explaining the results. No, but basically, there's no way right now that we can prove that the gravitational wave background that we're seeing is the result of binary supermassive black hole in spiral, right? That there's no kind of one-to-one for us right now. We need to look for individual continuous wave signals before we can be quite sure that is what we're seeing. But our signal that we're seeing is very much consistent with the background being from supermassive black hole binary in spiral. We see a little bit of that turnover that I mentioned that you would want to look for in the spectrum on the plot on the right. This kind of suggests that there are more interactions and that the supermassive binary black holes that are involved are more massive. So more frequent, more massive mergers increase the amplitude, the overall amplitude of the background, but then the turnover kind of tells you how much dynamical interaction is going on to help those mergers proceed. And so we're only at the very beginning of being able to kind of learn all of the astrophysics that we want from our observations. But it's pretty cool that we can even start to think about what we're learning about the larger universe through these observations. Yeah, and there's some details like we think that the signal is dominated by very high mass in spirals. we're looking at typical redshifts of 0.15 to 0.9 and separations at the sub-parsec, so 0.1 to 0.01 parsec level, right? We're not actually, this is an important point, we're not actually detecting the moment of in-spiral, right? This is a very long-term process. It takes us quite a long time to build up the signal, because what we're looking at is the in-spiral stage, not some kind of, event, I guess, if you want to look at it that way. We're not looking at the moment of merger. Okay, so there are also some very interesting things that you can think about if you want to talk about physics beyond the standard model. So a lot of these sort of interesting, phenomena that could explain dark matter. We're talking about like phase transitions. We're talking about inflation. A lot of these predict early universe, very low frequency gravitational wave signals. So the primordial gravitational wave background can sort of be thought of like the cosmic microwave background, right? It's even earlier though. So this is something that's being imprinted, and it would show us a very low frequency gravitational wave signal. There are all different kinds of sort of propositions here that you can look at. The summary is that we can't rule any of them out, right? That the data so far are consistent with domain walls, cosmic strings, inflation. And so we're not saying anything solid, basically, about these results. But with time, we'll be able to better sort of constrain the various interesting models. The takeaway here is just that there was a search for anisotropy in the background that did not show significant anisotropy. That will be one sort of very obvious indication that what we're seeing is from supermassive black hole binary in-spirals, is if there's like an overdensity in one part of the sky, because we're dominated by certain mergers. But we don't see evidence for that yet. That's not particularly unexpected. They also looked at limits on the signals from those individual binaries, so the continuous wave signals. Maybe some interesting possibilities, but nothing is significant yet. And so what we're seeing is sort of this background ensemble signal. Okay, and as I already mentioned, the IPTA is seeing very similar things. There were results from the Australian collaboration, the Europeans and the Indians working together, the Chinese Pulsar timing array, which is a very new collaboration. They're using the FAST telescope, which is a pretty amazing instrument. There are really exciting results from the Meerkat, so Meerkat, the South African array, coming very soon. So look out for that. And we are working really hard on combining all of our data sets in order to gain sensitivity. And so stay tuned in the next 1 to 2 years-ish for results from the IPTA. So very briefly, the kinds of things that we're thinking about right now are improving our instrumentation. Literally this week at the GBT, we're testing a new ultra-wideband receiver that goes from 0.7 to 4 gigahertz. So that's going to help hopefully double our timing precision with the GBT. We're also very involved in the DSA 2000. So this is a proposed array that is going through the process of, NSF mid-scale review right now. And so that would help us, we get about 25% of the time on that telescope. It would help us time hundreds of millisecond pulsars, which would be extremely important for sensitivity. And we could have much more frequent cadence than we have right now. And so we're hoping for kind of anything we can that gives us more telescope time, more sensitivity, more frequent observations. Everything that we can get is important. And that's all I've got. Thank you so much.
All right. Does anyone have any questions? We're thankful.
I have a question about like the different kinds of physics and astrophysics and how to disentangle them. So I was just wondering kind of what's the state of theoretical predictions, and like is the expectations that it is possible to disentangle those kind of by considering them separately, or will we really need to have a, cosmological simulations of galaxy formation and supermassive black hole mergers and like these different cosmologies with all of these different physics ingredients to be able to disentangle them?
Are you talking about, so just, I want to make sure I understand the question. Are you talking about the different kind of early universe phenomena, the beyond the standard model, or are you talking about?
Well,
are
I
you
guess
talking about
maybe okay. Let's see. My understanding was that like the reason why it's not possible to tell apart like all of these like different beyond standard model physics that you mentioned and just supermassive black holes in spiraling was that they have a similar signal like at this. So I was just wondering how to if there's some metric to kind of disentangle those.
Yeah, so part of it is gaining more sensitivity to the low frequency end, which is where a lot of these like characteristics will show up. And so right now, because the experiment hasn't, it's been going on for a long time, but it's not that long. And so as our kind of timing baseline grows, our sensitivity to the sort of spectral shape at those low frequencies will improve. And so that's an important factor in kind of disentangling the various kind of standard astrophysics, like the normal supermassive black hole binary and spirals from the kind of inflation cosmic stream type models. The other thing is like what I mentioned very briefly with the anisotropy. If we're able to sort of measure individual black hole mergers, we'll have more of a sense of the kind of level of contribution to our signal that those events have. And so we expect probably that the vast majority of our signal is from supermassive black hole binary and spiral, but we're not at a point right now where we have good enough kind of spectral characterization to say that with any, definite.
Right.
Yeah.
Okay. So, so that would be a kind of smoking gun signal. But in the absence of that, kind of how long would the time baseline need to be to characterize like the low frequency spectrum well enough to start disentangling those effects?
Yeah, that's a really good question. So I think we're hoping for more clarity on the time scale of like 5 to 10 years. Okay. That's kind of where we reach a threshold where these things can be disentangled better. Yeah, it's a little bit weird. I mean, we just like we have this exciting evidence, but it's really only kind of the beginning of the experiment. So we have to make a compelling case for continuing to observe as often and as much as we can. Yeah.
Great. Exciting.
Thanks.
Thanks for the nice talk. So 15 years down the road when, we have SK and these other, next generation telescopes, and we have maybe several hundred pulsars in the sample. What are do you have a sense of like the rate that we would be able to detect individual supermassive black hole binaries? And also, are there prospects for, so, in 15 years, Lisa will be observing too. Are there prospects for observing, the same source in spiraling in a PTA and then merging in the Lisa band?
So I don't think that there's enough overlap to do simultaneous observations or, simultaneous observations or whatever. But don't quote me on that, but I'm fairly sure that there's not enough frequency overlap for that. In terms of kind of rates or what we expect to be able to detect as the number of telescopes and the number of pulsars grow, there's really nice work, kind of simulation work that's been done. There's a paper from Nihan Pol and the rest of the folks in detection, sort of talking about what the prospects for detection over the next decades will look like. But I mean, I do know that we're hoping to gain individual, continuous wave sensitivity on the scale of 5 to 10 years. In terms of number of individual binaries, I mean, I think we're very overpowered by a limited number of very massive mergers. And so obviously it'll have a lot to do with what the actual mass distribution is, and what the underlying kind of frequency of events is. So I think that there's a fair amount of open question. But yeah, I don't have a more like quantitative answer than that.
Oh, okay. Also just I was rude and Googled the mass of Jupiter thing during your talk. And apparently it was like 10 to the minus 11 and 10 to the minus 10 like solar masses. So that's pretty crazy.
Pretty wild. Thank you, Allison. Yeah. Yeah.
Thanks for the great talk. This is, I guess, kind of related in that thinking about kind of down the line, but once assuming that you are able to start localizing some individual sources, will that allow you to go back and look at this cumulative signal and learn something more about like the mass distribution and also the like the mass ratio distribution of the binaries in the background population?
Yeah, that's a really interesting question. So like, will we be able to, with the knowledge, with the constraints we have of individual events, then apply that to our characterization of the overall spectrum, rather than just a signal at a particular frequency or whatever, and understand about the other components that are maybe not directly detectable? Is that sort of your question?
Yeah, well, I mean, it seems like on the one hand, it's like, assuming this is all this, yeah, it's from this background. On the one hand, it's frustrating not to be able to see individual sources. On the other hand, it seems like a really complementary thing where you are seeing the entire potentially population. And so are there more details that will be able to be?
Yeah, that is interesting. I guess it would be my suspicion that having constraints on the like amplitude of the signals from the individuals that we will be able to kind of pull from the background might be helpful. But at the same time, these are analyses that have to be done in tandem. It's not like a completely separate thing. And so I imagine that it'll be helpful with getting a better picture of kind of the distribution of masses involved in the ensemble of mergers, and kind of event rates. But I'm not sure exactly how. I think it's kind of more of a back and forth than it is like this is a separate kind of signal that we're detecting, and then we can apply it to characterizing the spectrum at our low frequencies on whole, if that makes sense.
Thank you.
Yeah, thanks.
All right. Any last questions for Thankful?
Sorry. Okay. Really, really dumb question. You said there's like 68 pulsars in a timing array right now, but there are some number of thousands in the Milky Way. So was that right? What's the process for a pulsar like gaining candidacy as a timing array member?
Yeah, that's not a stupid question at all. It's a really important question. We only know of about 400 millisecond pulsars. So of the ones, we wouldn't consider adding kind of normal slow pulsars to the array. We can't time them with high enough precision. But our selection of pulsars is quite boring right now. So almost all of them are just white dwarf millisecond pulsar binaries. They're not very high eccentricity. Most of them are completely sort of circular orbits. The pulsars don't glitch. They don't kind of, for the most part, have eclipsing behavior or anything like that. That's something we have started doing, is trying to figure out where we can kind of start breaking our rules and adding new pulsars to the array. So one of the things that we're doing is adding what are called spider pulsar binaries. And so these are highly accelerated binaries where there's a lot more kind of interaction, there's a lot more matter in the system. And so you're seeing sometimes these systems will eclipse. So you can just choose to not observe them during, that period over conjunction where it might be masked. And we know that even if we have to account for like higher orbital frequency derivatives, it doesn't take enough signal out of our gravitational wave sensitivity. Like it's not stealing sensitivity from the low frequency gravitational wave signal that we're looking for. It's completely fine to do. So even if we have to start kind of these more complicated modeling processes, we think that we'll be okay. But extremely boring set of pulsars as far as like the PTAs are concerned for the moment. Yeah.
Okay, we did have one question come up in the chat. The gravitational wave signal that was detected was described as being higher amplitude than expected. Any further info on why that is or how that will be resolved?
Yeah, so I mean, I think the way it'll be resolved is just with better spectral characterization from more observations over time and getting kind of a more thorough view of the entire landscape. In terms of, I mean, I think we're at a point right now where we can't really say anything definitive astrophysically about what the slightly higher amplitude means, because you already have to assume that you're already assuming that the signal that you're seeing is from supermassive binary black hole mergers. And so, I think that our kind of spectral characterization, as I've said several times, is going to improve quite a lot over time. But I hope I'm kind of getting at the question.
Yeah.
But we can't say anything like definitive right now. We just know that if this is the signal that we're seeing, there must be a lot more interaction and kind of higher masses than we were expecting.
All right, let's think thankful.